Okay. I think what we were gonna do today is talk about logarithms and exponential functions, because we use logarithms. You've seen logarithms. Can you remember a fair amount about them? Been a while, it wasn't rusty with them, but that exceeds what we expect somebody who hasn't had an analysis of pre-calculus course. Okay, so you had a very good algebra 2 course. Okay. So that allows us to talk a little bit more about logarithmic functions. We used them last time to solve some equations. So that's one thing they're useful. They're also useful for modeling things like hearing intensity versus perception. Okay, we're not even talking about that. But we do a graph of this function, and the graph is going to look pretty much like this. That's pretty familiar. Okay, now the inverse function. What we're going to have to do, go ahead and reverse the columns and sketch the graph. Okay, now you did very well with that. It looks very good. You have a graph, and your graph kind of looks like this. Well, let's draw a precise graph so we can really talk about the reflections and so forth. Okay. So 1/4 -2. Well, here's 1/4, and here's -2. Now this corresponds to the point -2 1/4 over here. Okay, and you can kind of see how it does. It's like we've switched the axes. It's also like we flipped the paper over. And you can think of how that works. So they're kind of use colors here. Apologies to anybody who can't see colors. I can't see all colors, maybe, but that's not the case here. And then we have 1/2 -1. Well, here's 1/2, and here's -1. And this point, of course, corresponds to the point -1 1/2. Then we have the point 0 1, 1 0, sorry, and that corresponds to the point 0 1. Then the point 2 1, which corresponds to the point 1 2. And finally, the point 4 2, corresponding to the point 2 4. On the graph of the exponential function. And well, we can draw a curve now. Okay. Let me draw this curve. And one thing about the curve is having switched the x and the y components, or the x and the y values. and not have this. Wow. That's such a pretty picture. Though. Just kind of. Okay. Yeah, but this one, with the words. Okay, go. Okay, so let's again try to make this point to this point. The secret in drawing the straight line through a point is to look at the point you're going for. I was actually looking up here where I was ultimately headed and everything around that. So go through this point. Okay. Still have to. Okay, what's this line? This line makes a 45-degree angle with both axes. And if assuming you have equal scales, I'm not sure how well yeah, I kind of managed that pretty well. Okay, here's the y equals x line. And the interesting thing is, and it's not hard to understand why. Might as well keep. Yeah. Oh, okay. This point is a reflection of this point across this line. The line that connects this point to this point makes a right angle with the y equals x line. Okay. And these 2 points lie at equal distances on opposite sides of the line. That's what we mean by reflection. Now, same thing up there. And here. And here. And that's kind of a neat picture. Even better if I have to take a screen. It's kind of important to understand that. If this is x, y, this is y x. Okay. Well, let's now just kind of confine our attention to this graph. Can you estimate based on your graph what the y value of this curve would be if x equals 3? Okay, now if I make an honest estimate here of what y is going to be if x equals 3. I come over here and it kind of gets. It's a little more than 1.5, so I'm going to estimate that this might be 1.6. Hey. I'm going to give these functions names. This function, of course, is your basic exponential function. Okay. Your base 2 exponential function. Your toolkit exponential function. This is log base 2 of x. That's what a log is. It's inverse to an exponential function. Let's say in general. Log base b of x is inverse to the b to the x. And I can improve that statement. That's it. Okay. Now to calculate log base 2 of x, your calculator probably allows you to cheat. Probably allows you to actually do log base 2. Okay, well, you're saying it doesn't. Okay, that's good. I don't allow that. Anyhow, if you're gonna calculate the log base 2 of a number, you're gonna use this rule. Now, every calculator made since in the last 40 years will do an LOG, which is your base 10 log, or an LN, which is your natural log. Doesn't matter which one you use. Okay. So you can always calculate. So use that to see if you can calculate log base 2 of 3. We estimated approximately 1.6 or 1.7. Okay, calculator. Log base 2 of 3 is log 3 divided by log 2. And that runs to 3 significant figures is 1.58. So our 1.6 and 1.7 was a perfectly reasonable estimate. Well, one thing you can absolutely definitely see is if you can sketch a really good graph of your base 2 log, at least 2 to the 4, you can make an estimate that is probably accurate to within about 1/10 of the accurate value. And you get a good feeling for the curve. And I always encourage estimates. However, if you want it precise, and many times you do, you want to do this. All right. A little bit more. Let's say that you have x equals log base 7 of x. Let me change that to 7. It's going to be easier to draw the log for smaller. Okay. Let's say that we want to do the log base 1.2 of X. Now, that's the kind of calculation we would get if we were working with an exponential population or an investment, which would be really nice, that have a growth factor or multiplier of 1.2. That'd be like 20% annual interest, 20% effective annual interest. Okay. 20% annual growth rate. So something that might arise. Okay. Well, no, it's actually just log, sorry. Again. What I wrote was correct, but I'm going to do. Base 2 log. And of course, this equals this. Okay. Let's use an estimate. To estimate log base 2 of 1.2. Even using your graph, you're probably going to be able to estimate that reasonably well. Probably within a tenth or so. So what do you get? Okay, so yeah, we see this. Okay. I can estimate log base 2 of 1.2. Of course, I go to calculator and get as many significant figures as I want. Okay. But I'm going to estimate it just to the nearest 10. Okay, this is 1 and this is 2, then 1.5 is about here. 1.25, but this in equal pieces. And 1.2 is maybe about here. So, you know, I come up to the graph here, and I come over here. And I get something probably between 1.2 and 1.3. And on honest estimate, my graph would actually be a little less than that, but I also take account of the fact that my curve is a little bit to the right of the 0.10. Okay. Okay, so let's do this. Okay, let's say let's say that our estimate came out to 0.25. We can't decide between 0.2 and 0.3. We know it's not 0.4. We know it's more than 0.1. Pretty sure it's more than 0.2. Not sure it's really 0.3. So we get this. Okay. I think that estimate's probably pretty close. Okay, then. F of X is 1 over 0.25 times the log base 2 of X. That's approximate. F of X is about 4 times log base 2 of X. Well, let's say we got a graph of the log base 2 function. Now I'm gonna draw a graph here. And the log base 2 function gets pretty flat. I'm gonna change the scale, use a Y scale where 2 is all the way up here. And 4 is here. Actually, that's a bad idea, so I'm not gonna do that. Okay. Because of what's coming up. Okay, I'm gonna put 2 here. I'm gonna put 4 out here, and I'm gonna put and 2 here, 1 here, 1 there, 1, 4. And -2 will be here, and -1 will be here. So our graph with this exaggerated scale for something like this. So here's my log base 2 of X graph. Based on this graph, can I make a graph of f of X, which is 4 times log base 2 of X? Okay, well, to vertically stretch, well, okay. 4 times log, here's log base 2 of X. How are we going to get 4 times log base 2 of X? How are we going to get the graph? Well, we could go back to the table and multiply all these numbers by 4. But we don't need to do that. You can see it on the graph. Okay, if I take a point, let's say here on this graph, then I can draw a little arrow. Let's use some color here. I can draw an arrow that represents the value of the function to this value of X. Because of course, you know, if this is X, then this is the value of f of X. If I want a graph of 4 times f of X, or, well, I'm using f of X for this, and f of X for this. Let's call this function y equals g of X is log base 2 of X. Okay. Now, if this is a value, any value of that, I can get the value of that in G, but I think it's G of X here. Okay. So the value of G of X is this much. Well, so is the length of this arrow. So the length of this arrow is equal to the value of our log base 2 function, which is our G of X function. Okay. If I stack 4 arrows of equal length, the length of each arrow is the value of G of X. And what I get over here is 4 times G of X. So what value 4 times G of X? So this would be a point on the graph of 4 G of X, which of course is f of X. Our f of X function is 4 times G of X. So for this value of X, G of X is this much, the value of f of X is this much. And I can do that from every point on the graph. But I kind of know the shape of the curve, so I want to do it for a few points. I'll go ahead and do it here. Except I don't know if I can get 4 of these arrows on the table. Under the ground. Yeah, it looks like that kind of. Okay, so here would be F of 4. I can take a point here. And of course, the point we're actually for 0, and we're y equals 0 is going to give me 0 for either function. Down here, I can go down here 1, 2, 3, 4. Then I can take these green X's. And I haven't done a great job of positioning these, but and I get a graph of my f of x function. Okay, it's a vertically stretched version of the log base 2 graph. So now I can do estimates. Now I said that this point, well, this point should have value 2. So this point, the point value should be 8. So I should have 8 here. Halfway between here and here should give me 4. This is 2. And then we have 1 and 3 and 5 and 7. And now I've got the scaled graph, not a very good one because the curve kind of gets a little hyper right here. Okay, the downward concavity gets a little bit exaggerated because I didn't locate these points all that carefully. Still, let's say now that we want to estimate log base 1.2. What the heck, 3. Now remember, let's go back. Let's see where we came from. We said that f of x is log base 2 1.2 of x. Okay. So this is a graph here of three is about here. So just eyeball it. If I start from this point and go through the graph and go over, what's it look like my value of y would be? Okay, eyeballing it without actually drawing the projection lines would have to be straighter than and more vertical and all that stuff. You have to be a little more accurate to draw, but be able to draw. But go up to here and over. You know, right there, I got like 6.8. or 6.7. Well, let's go ahead and try to draw a vertical line. Also, see, I kind of cheated over this way when I did this. So it's not good. But if I do my projection lines honestly, that comes out about 6.5. Now, that's not going to be a hugely accurate value. Yep, 6.5. Okay. According to your graph, which doesn't have your graph only goes from like 0 to 2 because you didn't have room to go much higher. Okay. Let's estimate log base 2. I'll estimate it my graph, you estimate it on yours. Log base 1.2, not log base 2 of log base 1.2 of let's see, here's 1, here's 2. Let's go 1.7. See what you get, and I'll see what I get. Okay. We've got an estimate, it was 3.7. I'm just gonna write that here. And let me do my estimate. I'm not gonna look. Halfway 5 would be about here. 0.7, I think is probably about there. 1.7. Okay. So if I come straight up from there and across, I did that honestly. Well, here's 2 and here's 4, so here's 3. Now here's my estimate. Here's 3 and here's 4. Halfway would be about here. And I'm estimating 3.75. Now my graph is bigger than yours. But remember, I'm the one that's drawing. Your graph is well drawn. And you got 3.7, didn't you? Okay, so we're in kind of agreement. Well, I'm demonstrating several things. Like the idea of a vertical stretch. I don't expect that this is going to be all that close to the log base 1.2 of 1.7. Okay, 3.75. Why don't I expect it? Because this 0.25 was estimated from that graph. Okay, that's a pretty good graph, but it's kind of hard to estimate some small numbers. So this could be 1 over 0.3, 1 over 0.22. Okay, wide range. So that 4 is very sensitive to how well we estimated this. So being that sensitive, I don't think 3.75 or 3.7 is going to be a great result, but I expect maybe it will be around 4, at least not too far away from 4. Okay, maybe closer to 3, maybe closer to 5. So can you punch it in now? Can you use your calculator to actually calculate log base 1.2 of 1.7? Okay, now the results we got are pretty well correlated with what happened in this graph. Okay, first of all, the 3.75 was fairly high. It was closer to 3. Matter of fact, it was like 2.9. Now, with all the questionable accuracies of estimates that we've used to build this estimate, because this estimate is based on another estimate. And it's a hand-drawn graph, so that isn't too bad. Now, notice how this graph was kind of too steep here and suddenly it didn't curve real smoothly. Okay. If it had curved real smoothly, which it might have done, these points were a little more accurately positioned. We might have had a little better estimate, but still it wouldn't have been that great. Now, the 6.5 that we estimated for the log 1.2 of 3, or that I estimated, was actually about 6.0, wasn't it? 6.0. Okay, so that wasn't too bad. But the graph had a change in it. Okay. Okay, well, enough of that. I wanted to demonstrate the vertical stretch and reinforce this rule. Very important. Now let's see what all this is good for. Let's say that we've got a population E of X equals 80 multiplied by 1.2. Instead of X, I'm going to use T for the variable. And again, that corresponds to an annual growth rate of 20%, right? So when will the population be 130? Now we can estimate that 20% of 80 is 16. So after 1 year, say we're up to 96, and 20% of 96 is about 19. So just using whole numbers, we get 115, and 20% of 115 is 23. That's going to get us up to 138. Okay, so sometime between the second and third year, T equals probably about 2.9. Okay, I think there's 1, 2, 3. Okay. Okay, so when is population 130? Well, to do that, we solved the equation. P of T equals 130. And that means that 80 times 1.2 to the T equals 130. Now, that's not an equation that you know how to solve. Actually, you kind of do, because you did some logs and you remembered quite a bit of it. Okay, so what do? We divide both sides by 80. And that's 1.5. It's 130 in the right side. So I kind of solved that in my head, and I was getting something closer. 2 years and 3. Okay, so that's 13/18. 13/8. Now, through the magic of logarithms, and I'm going to give you the rule in a minute, I'm just showing you how this is useful. I mean, it's useful in many ways, but, okay, 1.2 to 3 is 13/8, which means that T has to be 1.2 of 13/8. And I'm guessing that'll be 2.8 or 2.9 in that vicinity. Now, I'm going to give you a rule and relate it to the inverse function relationship. But first, let's go ahead and punch that into the calculator and see what we get. Well, I don't like the result much because it wasn't all that much in agreement with mine. Rounded to the nearest tenth, it's like 2.7. And I thought it'd be closer. Okay, so you probably need to talk to the people who created that app and tell them to make it more. Well, seriously, this is a log. 13/8 over the log of 1.2, which is about 2.7. Okay. Now let's see what we would have gotten if we'd have estimated that using the graph. If we use the graph, 13/8 is 1.625, which is pretty close to 1.7, which I already estimated here. I got an estimate of like 3.75. Whereas the actual should be only 2.9. Now, if I move over just a little bit from here and do an estimate, my estimate might come out 3.6. Now, changing from 1.7 to 1.625 doesn't seem like it would have changed this result all the way from 2.9 to 2.7. And it's a little less than 2.7, 2.66 or something. So I don't know. I have to reconcile that, but it's okay. We got the method, right? So we see a couple of things. First of all, estimating that this function should be about 4 times this function. Sketching a reasonably accurate graph of the log-base 2 function and stretching it by a factor of 4 gave us a graph that gives us reasonable but not hugely accurate results. Okay. We constructed this graph a little more carefully because I don't know, again, some of these arrows may be a little bit longer than this one. There are a lot of things that could go wrong. I wasn't particularly careful when I did that. The whole graphical picture, though, that's something I emphasize in pre-calculus and graphical pictures, but try to make sense of calculations. Okay. Anyhow, let's do another calculation. What is the log base 2 of 1.2? I think I saw it like 0.30 something. I saw that number on your calculator. Okay. Now, I estimated 0.25. Looked like it's between 0.2 and 0.3. And I was using a little more than just a graph. Straight line from here to here, you would get 0.2. Line has some concavity, so I knew it was a little more than 0.2. Concavity is pretty significant here. So I kind of use that too. That's pretty close. This really should have been 0.265. Okay. So the 4 should have actually been the reciprocal of that 0.265. Can you do the reciprocal of 0.265? One divided by. Okay, now the 4 held up pretty well, but the log base 2 of 1.2 is actually about 0.265, not 0.25, which means that 1 over 0.25, which would have been 4, should have been 1 over 0.265. That comes out 3.77, about 3.8. Okay. So the vertical stretch of this graph would have been a little bit less than it was, which partially explains why we got overestimates. Okay, well, so much for that. We do want to understand transformations with graphs. So that one of the things I wanted to talk about now is coming back to the nuts and bolts of exponential functions. Using logs to solve equations. You see an equation here. Could be a very practical equation that we would solve for t to estimate how long it's going to take our population to grow from 80 to 130. Can't be guaranteed because there's population in an uncontrolled environment. All kinds of things can happen, but it's going to be our best guess that in a little less than 3 years, our population is going to be 130. Okay. Right here is an exponential equation that we might want to solve for A. And that's equivalent to this log equation. Because if it was b to the x equals y, and I don't want to just use x and y because, you know, we have t's, we can have all kinds of things in the exponent. It's not always just x and y. But if this was x and this was y, this says that the point x, y is on the graph of b to the x. Okay. This says that y x is on the graph of log base b of x. Okay. So we're like reversing the roles of A and C. Now, it takes a little thought to do that. I'm just mentioning it. You don't have to master that. If I gave you 2 minutes to think about it, maybe you would. It's not that important. Although it's interesting, and eventually when you actually take the pre-calculus course, you'll be in a good position to really understand that, okay? And this is a quick introduction here. So that's not something that you really want to chat with. Okay. But this is because of the inverse function relationship. So the inverse inverse function relation implies all of this. We apply this to the equation It's in the form B to the A equals C, where MB okay, it's in the form B to the A equals C, where B is 1.2, A is your T, C is the 13/8. That's pretty straightforward. So A equals log base B of C. If T equals log base 1.2 of 13/8. In pre-calculus yesterday, this equation, or this function came up, okay? Now, this is supposed to be the velocity of somebody falling through the air. Yeah, free fall, okay? It's supposed to be 80 feet per second. Well, it's a bad model, but this essentially tells us that your terminal velocity would be 80 feet per second. Okay, that's still enough to kill you, but it's really over twice that. Okay, well, regardless of that. Question was, what's the velocity after 2 seconds? Well, T's your time. So you just put 2 in for T and you plug it into your calculator and you get it. Or you do a good graph, make a good estimate. So that's real straightforward. We just do V of 2, so replace T by 2, do the calculation. It actually comes out 25. I estimated 24. I estimated based on this graph. Okay. And I also know what the graph of velocity is going to look like because I know how that works. But that's not what's really important. What we want to do next is find out when the velocity is 7. Well, velocity is this, right? So replace this by 70. Here we've got, well, here's the equation again. Replace V of T by 70 and we get this equation. Well, this equation now. Well, this. That's smudged out of here. Okay. So we solve the equation. What we're going to do to solve the equation, well, we're trying to get T. We divide both sides by 80. And we're left with 1 minus equal to negative 0.02 T. And we subtract 1 from both sides. Okay. And 70 over 80 minus 1 is 7/8 minus 1, which is 7/8 minus 8/8, which is negative 1/8. So we get this equals negative 1/8. And then we multiply both sides by negative 1, and we get e to the negative 0.02 T equals 1/8. Then what do we do? That's in the form B to the A equals C. Okay, B is E. A is the negative 0.02 T, and C is 1/8. So we get log base E of 1/8 equals negative 0.02 T. So that T is the log base E of 1/8 divided by negative 0.02. Okay, now I use natural log because that's what log base E is. And log base E is natural log. And you have a natural log function in your calculator. So, and I never did estimate what speech would be. Yeah, for the time. I'm gonna save myself the embarrassment of doing that estimate. Okay,